Welcome back. In this video, we're going to take a look at how we determine the location and the size of an earthquake. Both of these topics are fully discussed in the earthquakes chapter, but you're going to get some hands-on experience. In the last video, I described the types of seismic waves. These should look very familiar to you. As I said, you can determine how far you are away from the epicenter of the earthquake by measuring the time difference between the arrival of the P and the arrival of the S wave. In this animation, the P wave is the fast car and the S wave is the slower car. Notice how the P wave arrives before the S wave. In the top example, the S wave arrives 0.5 seconds after the P wave. In the bottom example, the finish line is farther away. The P wave arrives first again, but this time the S wave arrives 0.75 seconds after the P wave. Notice how the farther the finish line is, the longer the lag time between the arrival of the P and the arrival of the S wave. That is exactly what we see in real life with seismic waves. Here is a seismogram. Along the x-axis is time and the y-axis is amplitude. Notice how the difference in the arrival times is just the S wave arrival time minus the P wave arrival time. In this case, the change in time equals 9 seconds. Now, using this graph, if you take this lag time, also known as delta t in the graph, you can find the distance to the epicenter using this graph. You can also find the distance using the equation at the bottom. Remember that scientists can collect data and organize it in a table. That data can also be graphed, and from the graph, an equation can be derived. As you can see from this graph, there is a line. The equation of this line is used to make predictions. We can plug it in our delta t and multiply it by the slope of the line, which is 8.25 kilometers per second, to find the distance denoted as d in this equation. Notice that you can find the distance either graphically using the first method or algebraically using the formula at the bottom. In activity, I will be giving you some data and you will find the distance those localities are from the epicenter of the Earth. But you know that in order to find the epicenter, you need to triangulate its position. In this example, the epicenter of the July 4th earthquake was triangulated using data from 3 seismometers. The seismometers are located at CSUSB, UNLV, and UC Santa Barbara. Each locality knew its distance from the epicenter but did not know the direction. Using circles around each seismic station, one is able to triangulate the position of the epicenter. It is where all 3 circles meet at one point. Because I didn't send you home with a compass to make circles around seismic stations, you'll be using the data to determine the epicenter of the earthquake. For instance, after an earthquake, CSUSB, found on the left side of the table, calculated that they were 76 kilometers from the epicenter. Oxnard calculated that they were 125 kilometers from the epicenter. And Pomona, my fair city, is located 46 kilometers from the epicenter. All that data points to Irvine being the epicenter of the earthquake. You will be doing this with the data I give you in the activity. Next, we will look at determining the size of an earthquake. People always want to know how big an earthquake is. Before people could calculate and measure it, earthquake sizes were based on how they were felt and how much destruction there was. Giuseppe MERCALLI, an Italian volcanologist, developed the intensity scale in 1902 based on the amount of destruction from an earthquake. Then, a modified version of the scale was developed using California buildings as the standard. This became known as the modified MERCALLI scale. The intensity, though, is based on how far away you are from the epicenter of the earthquake and is not a single number indicating energy release. Charles Richter, along with others at Caltech, remember Benno Gutenberg, developed a magnitude scale in 1935. It is calculated by measuring the amplitude of the largest seismic wave recorded on a seismogram. Because seismic waves weaken as the distance between the hypocenter and seismograph increases, Richter developed a method that accounts for the decreasing wave amplitude with increased distance. Different recording stations often obtain slightly different magnitudes for the same earthquake because of the rock types through which the waves travel. Richter used a logarithmic scale to express magnitude because large earthquakes produce thousands of times larger movement of the needle in a seismometer than those generated by weaker tremors. So, for example, a magnitude 5 earthquake has 10 times more shaking and hence movement of a seismometer than a magnitude 4 earthquake. A magnitude 6 has 100 times more movement of that needle than a magnitude 4. Additionally, each unit of increase in Richter magnitude is about 32 times more energy released. So, if we calculated energy release and used the magnitudes in the previous example, a magnitude 5 earthquake has 32 times more energy release than a magnitude 4. A magnitude 6 releases 1,024 times energy than a magnitude 4, which is 32 times 32. Richter and his team developed a great way to describe an earthquake using a single number. But the Richter scale has its limits. Very large and very small earthquakes are not adequately represented in the seismometer. In 1979, Hiro Kanamori and Thomas C. Hanks, no, not that Tom Hanks, described a concept called moment magnitude, which more accurately measured the total energy released during an earthquake. The moment magnitude, known as M sub W, is calculated by determining the average amount of slip on the fault multiplied by the area of the fault surface that slips. The moment magnitude provides an estimate of the earthquake size that is valid over the complete range of magnitudes. This was lacking in other magnitude scales. So let me guide you through how the Richter magnitude and the moment magnitude are determined. In the activity, you will come to a question that asks you to determine the Richter magnitudes of 3 separate earthquakes. You will use this figure right here, which is called a nomogram. Notice how the S minus P wave arrival time is on the left column and the maximum amplitude is on the right-hand column. In the middle is the magnitude of the earthquake. The dashed gray line is an example. Delta T is 4 seconds and the amplitude is 5 millimeters. A line from one to the other crosses the middle at a magnitude of 3. Now you give it a try. If the difference in the arrival time of the S and P wave is 2 seconds and the amplitude of the largest wave is 0.9 millimeters, what is the magnitude of the earthquake? Did you get the right answer? The magnitude is 1.5. You will have more practice on the worksheet. Notice in the green example, the amplitude of the largest wave that is measured on the seismogram is supposedly 10,000 millimeters. Well, that converts to 10 meters. There is no seismogram that is that big, so this had to be extrapolated from a normal size seismogram, which is certainly not 1 meter wide, let alone 10 meters wide. Remember when I said that the Richter scale is not very accurate when it comes to magnitudes greater than 6 or smaller than around 2? This is why. Now let's look at determining the moment magnitude of the earthquake. With this graph, all you need to know is the length of the surface rupture when the earthquake happened. Let's say that you visited the epicenter of the earthquake and measured a 35 kilometer, that's 21.7 miles. Notice where the 35 kilometer is on the x-axis. It is a logarithmic scale. By drawing a straight line up to the best fit line and then drawing a straight line from there to the y-axis, you can determine the magnitude, which in this case is 6.9. Whenever you use a graph to find an answer, you better believe that there is a corresponding equation, and here it is. If you take the log of the surface rupture length, multiply it by 1.6, and then add to it 5.08, you will get the magnitude of the earthquake. Voila! We can do one more fun thing with this data. We can estimate the intensity of the earthquake in this area by looking at the relationship between the surface rupture length and the amount of horizontal acceleration there was on the ground when the earthquake happened. In our example, the ground rupture was 35 kilometers and the magnitude of the earthquake was 6. Find the 35 kilometers and draw a line up to the curve that represents a moment magnitude of about 6.9. Then draw a line straight across to the y-axis. The horizontal acceleration is 0.1. G equals 0.1. Now moving to the modified Mercalli scale, match that 0.1 G to the correct intensity, and there you have it. It was a very strong earthquake. Damage is considerable in poorly designed structures, but negligible in buildings of good design and construction. In the activity, you are given data and asked to find the moment magnitude and the intensity. You will be doing all of this in the activity I posted on Canvas. Your book also has some helpful resources describing all of the information I just went through. Enjoy this activity. There aren't a lot of people in this world who know how to determine earthquake magnitudes. You are now part of an elite group. Make it a great day and keep shaking.